Welcome my dear learners for this course on heat transfer. In this final module we were discussing on heat exchanger. So far we have discussed about the effectiveness and NTU technique for analyzing the heat exchanger. In our previous lecture we have derived an expression for effectiveness NTU relation for parallel flow heat exchanger. In today's lecture let us continue from the point where we have stopped in our previous lecture. That is, I am going to derive an expression for effectiveness NTU method for counter flow heat exchanger. Come, let us derive expression for effectiveness NTU method for counter flow heat exchanger. That is case B, effectiveness NTU method of heat exchanger analysis for counter flow heat exchanger. If I take counter flow heat exchanger, the direction of flow of hot and cold fluid will be opposite to each other like this. Let us have cold fluid inlet here and cold fluid outlet here. Now if I plot the variation of temperature over the entire length of the heat exchanger, it will look like this. That is, we have temperature versus length profile. If I plot, the hot fluid will lose heat in the direction of flow and cold fluid will gain heat in the direction of flow. So this is cold fluid inlet, this is hot fluid outlet, this is hot fluid inlet and this is cold fluid outlet. So direction of flow is opposite to each other. Hot fluid is flowing from left to right, whereas cold fluid is flowing from right to left. So let us take this difference as delta T2 and this difference as delta T1. And for analysis, let me consider an elemental length dx at a distance x from the left end. That is, let us have an elemental length dx at a distance x. So this is the overall length of heat exchanger L. Now in the elemental length, let us have the bulk temperature of hot and cold fluid as TH and TC be the bulk temperature of the hot and cold fluid in the elemental length dx, and let us take this difference as delta T. This difference as delta T, that is TH minus TC. Now if I write the temperature difference in the elemental length for hot and cold fluids, so from left to right, if I take the difference out minus in, THO is less than THI, so therefore the temperature difference will be negative, minus dTH. So similarly here, if I take the difference, here, so this difference will be again what? This is less than this, so therefore this is again minus dTc. So in the positive x direction, if I take the difference of temperature for the elemental length for hot and cold fluid, both will give us the negative difference. So minus dTH and minus dTc. Whereas bulk temperature are TH and TC, that difference is delta T. Now the terminologies what we have used in our previous lecture, let us retain the same terminologies. Now delta T1 will change to THI minus TCO, delta T2 will change to THO minus TCI, correct? And delta T is TH minus TC. Let us retain the same terminologies. Now let us derive effectiveness NTU relation for counter flow heat exchanger. To derive that, let me consider the elemental length dx, analyze it and integrate over the entire length. That is, consider the elemental length of heat exchanger dx at a distance x at a distance x as shown in the figure of temperature versus length profile. Now for the elemental length, the rate of heat transfer dq can be written as UdA delta T, right? Take it as equation number 1, where delta T is what? Delta T is bulk temperature difference of the elemental length, that is Th minus Tc. Take it as equation 2. Now for the elemental length, heat lost by hot fluid is what? Heat lost by hot fluid dq is again negative, right? Minus Ch dTh. Similarly, heat gained by cold fluid dq is also written as minus Cc dTc, because here the negative sign does not mean that heat is losing. This means that the cold fluid is flowing in the direction opposite to that of hot fluid. Here negative sign indicates heat lost by hot fluid. Here negative sign indicates the cold fluid is flowing in the direction opposite to that of hot fluid. Don't get confused. Now, therefore, what I can write for dTh and dTc? So therefore, dTh can be written as what? Minus dq by Ch. Take it as equation number 3. And dTc can be written as what? dTc is minus dq by Cc. Take it as equation number 4. Now use equation 3 and 4 to move further, similar to what we have done in our previous lecture, that is for parallel flow heat exchanger. Now consider equation 2 and differentiate it. Differentiating equation 2. If I differentiate equation 2, d of delta T is equal to dTh minus dTc. Now substitute the value of dTh and dTc from equation 3 and 4. From equation 3 dTh, from equation 4 dTc. So what I will get? d of delta T is equal to minus dq by Ch. Minus of minus is plus dq by Cc. dq by Cc. So now if I take dq common, so I will get d of delta T is equal to, so if I take minus dq outside, I will get minus dq of 1 by Ch minus 1 by Cc. Correct? Yes, right. Now I can substitute for dq from equation 1. Substituting dq from equation 1, substituting dq from equation 1, I will get d of delta T is equal to minus UdA delta T of 1 by Ch minus 1 by Cc. 1 by Ch minus 1 by Cc. Now rearranging the term, I will get d of delta t by delta t is equal to minus u of 1 by ch minus 1 by cc dA. Now integrating on both sides, we have integrals from 1 to 2. D of delta t by delta t is equal to minus u of 1 by ch minus 1 by cc into integrals from 0 to a dA. Now if I integrate, I will get this of the form 1 by x, so therefore I will get log x ln of delta t 1 to 2 is equal to minus u, integral of dA is a, limit is from 0 to a, so therefore I will get it as a into 1 by ch minus 1 by cc. So this can be written as log a minus log b is log of a by b, that is ln of delta t2 by delta t1, which is equal to minus ua 1 by ch minus 1 by cc. So therefore delta t2 by delta t1, so delta t2 is tho minus tci, tho minus tci divided by delta t1 is thi minus tco, thi minus tco. This is equal to e to the power of minus ua times 1 by ch minus 1 by cc. Let us take this as equation number 5. Now if you carefully observe, I have THO and TCO in this equation. The main aim of using effectiveness NTU method is to get rid of THO and TCO. So therefore use the definition of effectiveness and replace THO and TCO and bring in effectiveness into this equation. So if I use the definition of effectiveness for hot and cold fluid and replace THO and TCO by effectiveness, I will get now moving ahead, using the definition of effectiveness for hot fluid, we have effectiveness is equal to CH THI minus THO divided by C minimum of THI minus TCI, correct? So now I want THO. If I simplify for THO will become THI minus epsilon times C minimum by CH THI minus TCI, correct? Take this as equation number 6. Similarly for cold fluid, if I write, I have for cold fluid we have epsilon is equal to Cc times TCO minus TCI divided by C minimum of THI minus TCI. Therefore TCO will become, TCO is equal to TCI plus epsilon times C minimum by Cc THI minus TCI. Let's take this as equation number 7. Now use 6 and 7 in equation 5. So using equation 6 and equation 7 in equation 5, if I use these two equations in equation 5 and eliminate THO and TCO, so I will get THO can be written as THI minus epsilon C minimum by CH, THI minus TCI minus TCI divided by THI minus TCO will be TCI minus epsilon C minimum by CC THI minus TCI. So this is equal to e to the power of minus UA of 1 by CH minus 1 by CC, 1 by CH minus 1 by CC. So now I can rearrange the term THI minus TCI, THI minus TCI. So if I do that, I'll get THI minus TCI common, THI minus TCI, THI minus TCI common times 1 minus epsilon C minimum by CH divided by THI minus TI, THI minus TI. If I take common, I'll end up with THI minus TCI, taking it out, times 1 minus epsilon C minimum by CC. This must be equal to e to the power of, let me multiply minus sign inside. If I do that, I'll get 1 by CH plus 1 by CC. It will become minus 1 by CH, right, and plus 1 by CC. So it will become, if I multiply minus sign inside, I left out with e to the power of UA, e to the power of UA times 1 by CC minus 1 by CH. I multiplied minus sign inside and simplified. Correct? THI minus TCI, if I take out 1 minus epsilon C minimum by CH, correct? So here I left out with THI minus TCO minus TCI minus, correct? Perfect. So now I can cancel off these two. So why I have done this is because the final expression should be in the form 1 minus C. As we all know, CH we are assuming it as C max and CC we are assuming it as C minimum. I should get it in the form of 1 minus C. So therefore I have multiplied negative sign inside. Now to make simplification further simpler, take the reciprocal of this. If I take the reciprocal of this, I can write it as, take this to numerator, that is 1 minus epsilon C minimum by CC divided by 1 minus epsilon C minimum by CH is equal to 1 divided by e to the power of UA times 1 by CC minus 1 by CH, 1 by CC minus 1 by CH, because I want minus NTU in the standard equation. So therefore I take it to reciprocal. Now if I take this to numerator, e to the power of x, this is of the form 1 by e to the power of x, I can write it as e to the power of minus x. So hence further simplification will yield us 1 minus epsilon C minimum by CC divided by 1 minus epsilon C minimum by CH is equal to e to the power of minus UA 1 by CC minus 1 by CH, correct? 1 by e to the power of x, I wrote it as e to the power of minus x, that's all. I have not done anything. Now let us assume the same simplification, that is Cc as C minimum and Ch as C maximum, and the heat capacity ratios as C minimum by C max, hence it will be Cc by Ch. Cc by Ch. If I introduce that, C minimum will get cancelled, so I left out with 1 minus epsilon divided by 1 minus C minimum by Ch is C minimum by C max, that is C. So 1 minus epsilon into C, this is equal to e to the power of minus UA, take Cc common, it will be 1 minus Cc by Ch. I got what I required. Now eliminate this equation 5, which is not necessary, so thereby I can arrive for the equation. So now I want to get equation for epsilon, right? So therefore cross multiply this and simplify, that is 1 minus epsilon will be equal to this into 1, that is e to the power of minus UA by C minimum times 1 minus C, this into this, minus epsilon C e to the power of minus UA by C minimum into 1 minus C, right? Now I want epsilon, answer for epsilon, so therefore I will take this here, or I will take epsilon this side. I will take epsilon this side. I left out with 1 minus e to the power of minus NTU times 1 minus C is equal to, I will take epsilon here, it will be epsilon minus epsilon C into e to the power of minus NTU times 1 minus C. Now take epsilon common, so that is epsilon, if I take common, I will get 1 minus C into e to the power of minus NTU times 1 minus C. So therefore I end up with effectiveness for counterflow as 1 minus e to the power of minus NTU of 1 minus C whole divided by 1 minus C into e to the power of minus NTU of 1 minus C. So this is the required equation for effectiveness for counterflow heat exchanger. You can verify from your data handbook, that is page number 159 of CP Kothandaraman heat and mass transfer data handbook written by CP Kothandaraman. Refer page number 159 in 8th edition, that is for heat exchangers. You will get this equation for effectiveness for counterflow heat exchanger. So thereby we have derived effectiveness NTU relation for counterflow heat exchanger in this lecture. So before concluding this lecture, I want to give some very important note for special cases. That is, if I move ahead for special case, before moving ahead, let me pause this video for a while so that you people can copy it down. Now moving ahead for special cases, if I move for special cases, first let us recall effectiveness for parallel flow. effectiveness for parallel flow that we have derived in our previous lecture, that is 1 minus e to the power of minus NTU 1 plus C divided by 1 plus C. Effectiveness for counter flow that we have derived in today's lecture, that is effectiveness for counter flow is given by 1 minus e to the power of minus NTU of 1 minus C divided by 1 minus C into e to the power of minus NTU of 1 minus C. So these are the expression for effectiveness NTU for parallel flow and counter flow arrangement. Now in case 1, for boiling and condensation, for flow boiling and flow condensation, for boiling and condensation heat transfer, for boiling and condensation heat transfer, temperature is constant, right? That is in case of evaporators flow boiling. In case of condensers flow condensation, temperature is constant, only phase will change. So since temperature is constant and phase is changing, Cp will approach what? Cp will approach infinity. So therefore, what is the value of Cmax? Cmax will also approach infinity. Hence, the value of C, that is C minimum by C max, will become 0. So substitute this to above equation. So for flow boiling and flow condensation, the effectiveness for parallel flow will be what? Effectiveness for parallel flow will be, put C is equal to 0. So put C is equal to 0. 0 and anything will become 0, 1. 0 also if I put 0, effectiveness for parallel flow will be equal to effectiveness for counter flow. Both will turn out to be 1 minus e to the power of minus NTU. Kindly make a note of this. Next, if I go for second very important case, that is if C is equal to 1, that is C max is equal to C minimum. In such cases, if you carefully observe, for parallel flow, if I put C is equal to 1, I will end up with 1 minus e to the power of minus 2 times NTU divided by 2. Done. Whereas for counter flow, if you observe, put C is equal to 1. If I put C is equal to 1 and if I put C is equal to 1, e to the power of 0 is 1, 1 minus 1 is 0. E to the power of 0 is 1, 1 minus 1 is 0. This is of the form 0 by 0, that is indeterminate form. Whenever we have indeterminate form, we have to use L'Hospital's rule. So using L'Hospital's rule, if you simplify and conclude, the expression for counter flow heat exchanger will be given by NTU divided by 1 plus NTU. Kindly make a note. This is very, very important. Otherwise, you will get the answer as indeterminate form. So this is the relation for counter flow heat exchanger if C is equal to 1. That is, the ratio of heat capacity rates is 1. Then effectiveness for counter flow heat exchanger is given by NTU divided by 1 plus NTU. With these special cases, I want to conclude this lecture, wherein which we have discussed effectiveness NTU relation for counter flow heat exchanger, and also I have discussed about some special cases. This effectiveness NTU can also be read through graph, which is available in our data handbook. So I will be referring Heat and Mass Transfer Data Handbook written by C.P. Kothandaraman. I will be using 8th edition. So if you use data handbook for the values of NTU, directly from graph we can get the value of effectiveness, or else for more accurate results we can use these correlations. That's all from this lecture. Thank you all.